Hi folks, welcome to our review for our final for Calculus 1. As always, there's a chat box over on the one side. You can always type in your questions and whatnot for this review. So if you see something along the way you just aren't sure about or whatnot, or you want to learn about, please ask your questions right away and I'll be happy to answer them as best I can. So last time we reviewed just some basic problems calculating derivatives, integrals, and limits. Well, now we're going to put all that together in all these applied problems. So the first case would be sketching the graph of a curve. And how do we actually go about doing that? Well, first things first, what we should always be able to do right out the gate is we should be able to find the place where you plug in 0 and what you get. So you'll get cube root of 1 over 2, right? So in that case, and just so we can see it, let me be a little bit more clear. So just a reminder, all we did is plug in 0 for the x's, so you get 0 plus 1 over 0 plus 2, where our function f of x is right up here. Okay, so this equals the cube root of 1/2, as I just mentioned. The other thing you should be able to find is when that equation equals 0. So what this first part says is that we have the point 0 and then the cube root of 1/2 on our graph. The second part that we should find is when that whole equation equals 0. So this will be our x-intercept, or possibly x-intercepts, just depending upon what we're dealing with. But in this case, you can immediately cube both sides and see that this implies that 0 equals x plus 1 over x plus 2. Well, that means that 0 has to equal x plus 1, because we can't have the denominator be equal to 0. We'll talk about that in just a second, and we'll deal with that scenario. But so 0 equals x plus 1, so that implies that x equals -1. So what that means is that we have the point -1, comma 0 on our graph. Alright, so far so good. Well, the next component that we're going to need is asymptotes. So that was our first part. And we don't have to do them in this order, but it helps. So asymptotes is when the denominator equals 0, or when the root is undefined. Well, not necessarily when the root is undefined, but that would be the domain. So checking the domain essentially is what we're checking for here, because everything cube root wise would be positive, negative, it's always defined. So now what we need to do is set the denominator equal to 0. So you have an asymptote when x plus 2 equals 0. So x equals -2 gives us an asymptote. So this means that value is not in our domain, right? Because that would be where the denominator equals 0. So what we need to do is we need to check out when the limit as x approaches -2 from the left of f of x is, and also the limit as x approaches -2 from the right of f of x. And this will tell us the behavior of our graph. Well, notice when we plug in -2 into the x plus 1, you're going to get a negative value up top. And then if we're approaching from the left of -2, that means some number less than -2, meaning like -2.001. So you get another negative in the denominator. So negative divided by negative makes a positive. So this would be positive, and then since this is an asymptote, we're actually approaching positive infinity. There's no exact value. You have basically something approaching 0 on the denominator and something approaching just some number that's negative in the numerator. So, but it's approaching 0 from the left-hand side. On the other hand, when we approach -2 from the right, notice the top is still negative, but the bottom, so like -1.9 would be an example. If you go -1.9 plus 2, that's -0 or positive 0.1 in this case. So negative divided by positive will make a negative infinity. So we have that for our vertical asymptote, right? And the other piece that we're going to need here is our good old-fashioned horizontal asymptotes. Well, if we take the limit as x approaches infinity of f of x, that's the same thing as taking it inside the cube root for our limit, because that's a continuous function, the cube root is. So the limit is x approaches infinity of x plus 1 over x plus 2. Well, we could just use L'Hopital's rule on that inside. So L'Hop, and so that's just the cube root of 1 over 1, which is just equal to 1. The same exact thing happens in the negative infinity case, so there's no difference really. So you have cube root, the limit as x approaches negative infinity. Then we have x plus 1 over x plus 2. You have negative infinity over negative infinity. You can use L'Hopital's rule once again, and you'll get cube root of 1 over 1 again. We drop the limit because it just turns to a constant right away. So this is 1 as well. So now we have some horizontal asymptotes. Okay, well, we're in pretty good shape now. We have the points when our intercepts occur, we have the asymptotes, how the behavior is around the asymptotes. So it sounds like just the function value stuff, we've got that taken care of. So now we got to start to find other things like the critical values and stuff like that. Okay, well, if that's the case, well, when does f prime of x equal 0 or undefined? F prime of x equals 0. Well, notice you have a 1 in the numerator, and so that would happen never. So because you have a 1 in the numerator, that's not going to happen. But we do have f prime of x is undefined. Sorry about the misspelling there. When, well, 3 over the cube, or 3 cube root of x plus 1 squared x plus 2 to the 4th, when that equals 0. Well, notice you can get rid of 3, you can get rid of the cube root, and so basically all this boils down to it's undefined when x plus 1 equals 0 and x plus 2 equals 0. So that means this is undefined when x equals negative 1 and also negative 2. Okay, makes sense on the negative 2 because you have an asymptote there. It should probably be undefined. Otherwise we had something interesting happening. But the x equals negative 1 is kind of neat because we have actually, that's one of our intercepts corresponding to that point. And so if you do have critical values, always try and find the actual function value according to that critical value, if it's reasonable, right? So that's something to kind of keep in mind. So in the other case, we have f double prime of x. So let's look at that second derivative. It equals 0 when negative 6x plus 8, so when the numerator of that second equation for the derivatives, and notice what we're working with for the derivatives. First derivative was given to us right here, so sometimes you might have to work it out and simplify it. Just depends upon the function given. But in this case, we have that already. And so notice, what does this do? Well, this is 6x equals negative 8 would be a solution. And that means x equals negative 8 over 6, which equals negative 4/3. Okay, so now with that value, notice that's not an asymptote, it is in our domain, so we can actually find that value. F of negative 4/3 and what does that equal? Well, that should equal, we plug it in, we get cube root of negative 4 over 3 plus 1 divided by negative 4 over 3 plus 2. Right? So notice that should be the same thing as the cube root of the top becomes negative 1/3. And what does the bottom become? Well, that'll be 2/3. So notice, after all this is said and done, the 3 would come up top and cancel off with that piece, and so you get, at negative 4/3, you get the cube root of negative 1/2. Right? So that kind of actually is very similar. You have negative cube root of 1/2. Remember, our y-intercept was actually the cube root of 1/2. So you have some similarities going in there in terms of what's happening with our graph. And so last but not least, f double prime of x is undefined. When, notice we'll need the denominator to equal 0, so we'll have x plus 1 equals 0 and x plus 2 equals 0. All right, granted you have an x plus 1 to the fifth, well, you take the fifth root, that goes away, and you still have 0 on that other side. So basically that's the same as the first derivative. You have negative 1 and negative 2 are the values that do that there. Okay, so now I think we are ready to graph this thing. Let's go ahead and take a look. So we have our graph set up in terms of what's going on, and let's list some of the things from the previous side. So let's look. First thing, we have 0 cube root of 1/2. So we have 0 and then the cube root of 1/2. That's on there. And then I believe we had negative 1 and 0 if we look back. All right. So negative 1 and 0. We had x equals negative 2 is a vertical asymptote. So vertical asymptote at x equals negative 2. And our left-hand limit, so as we approach negative 2 from the left of f of x, so our left-hand limit at that vertical asymptote was positive infinity, I believe. And I also believe our right-hand limit was equal to negative infinity. We can double check that in the previous page. We also have the limit as x approaches infinity of f of x, so the horizontal asymptote. And we can put plus or minus because they were both the same value. They both ended up equaling 1. Okay? So we're in pretty good shape thus far. What else do we have? So we had a critical point when x equals negative 1 and negative 2. So let's put f prime of x undefined, along with f double prime of x undefined at x equals negative 1 and negative 2. So, and notice we already had the negative 1 value there. We had negative 2's an asymptote, so we don't have to plug that in. But the only other thing that we had is a possible point of inflection. We haven't checked it out yet. At the point, well, let's take a look as to where our possible point of inflection was. Notice it was negative 4/3 for the x value. We got the cube root of negative 1/2. So negative 4/3 for the x, and then I'll put the negative out in front of it now because you can do that with the cube root. And we have negative cube root of 1/2. So now writing down these derivatives, we're going to have to kind of choose on point placement as well. But notice the furthest left we really go to is negative 2, it seems. Granted, there's going to be a lot more stuff to the left, so I don't need to jam a whole bunch of stuff in here. And so just to keep the spacing somewhat nice, we'll go negative 1 and negative 2 here. And so that means we'll put 1 here and 2 here, and then you can continue on out forever and ever as need be. Alright, and so that means also we'll have 1 here, 2 would go right about there, negative 1, negative 2, and let me continue this line on down just a little bit more. So it's really crowded up in here, but we'll figure out what happens in just a second in terms of how this graph looks. So the cube root of 1/2, notice we have negative 1, 0. Let me put this in red actually, So that's going to be right in here. Cube root of 1/2, that's going to be somewhere between 0 and 1. As you take a cube root of a number less than 1, you're going to get closer and closer to 1. So cube root of 1/2 will look probably somewhere around there. And then you have -4/3, so that's between -1 and 2, and then we're going to be close to -1 on that side. So split that into thirds. This would be that other point that we were just talking about. Okay, so there's some points on our graph. We're in pretty good shape with those. We have a vertical asymptote at x equals -2, so in order to indicate that, I'll just draw this red line, dotted line, meaning it's not included in the graph, but it goes on forever and ever. Okay, and now we're kind of ready to draw some points on the curve here. So we'll have two different number lines, and what are these number lines going to represent? Well, everyone has their own way of kind of representing these things. You can draw the boxes or whatnot. The way I like to do it is I put x and f prime of x, and I put x and I put f double prime of x. So I just write all the main points just to try and hit it home. So you have -2, even though it's only -2 and -1. Sometimes I like to put the -4/3 in there, but technically all we need the -4/3 on is with that second derivative. So -4/3, -1, and -2. Now, to keep this in mind, we probably need what those derivatives are, so I'll actually go back real quick and try and get those. I think this one was 1 over, oh gosh, I think it was something like cube root. Maybe it had a 3 involved, but there was a cube root involved. And it was like an x plus 1, the quantity squared, and an x plus 2 raised to the 4th. Something around those lines. Let's double check to make sure. Yeah, there was a 3 there, but okay, yeah, so good. 3 in that one. So we have a 3 times all that. That's not going to make much of a difference. In the f double prime of x, there was a -6. Whoop, is it not right in there? Okay, there you go. -6x plus 8. There we go. For some reason, I didn't want to write in that corner. Then I believe we have a 9. We have a cube root. I think it goes x plus 1 to the 5th and x plus 2 to the 7th. This one will be a lot more interesting than the others. So, as long as that's the case, yep, we're good. Okay. So we have those written down. Now you can make a little sign chart, as I said, or whatnot. The main thing to understand is I'm putting a u here above the -2 and above the -1, meaning it's undefined. And then for the -4/3, we know that it's going to equal 0 on that second derivative. So, looking forward from here, the nice part on the first one, so when we look at the derivative, the first derivative, what do we have happen? Well, you have 1 over 3, that's always positive, and then I'm squaring something and I'm taking something to the 4th. Well, if I square something, it always turns positive. If I take it to the 4th, it always turns positive. So every single value down below on the first derivative is positive. What does that tell us about the function? So this tells us that f of x is increasing. For all x not equal to -1 and -2. Okay? Or let me be a little bit more careful. It's increasing on so we'll go from -infinity to -2, -2 to -1, and then our last part would be from -1 to positive infinity. Okay? Questions on that? So now it's a lot more interesting when we plug in values like -2. For this beyond -2, so something to the left of -2. So say from -infinity to -2, we got to pick a value and plug it into this equation for all the x's. But all we care about is whether this thing is negative or positive. So say we had -4, for example. If we plug in -4, notice the first one we get a negative, But a negative times a negative makes a positive in the numerator. So we'd get a positive divided by, well, you'd have the 9 and the cube root aren't going to make a difference. So you have negative 4 plus 1, that's going to be a negative, and then raised to the 5th is still negative. X plus 2, so negative 4 plus 2 is negative. Raised to the 7th is still negative. Negative times a negative makes a positive. So you have positive divided by a positive. That means this thing is positive. So that means we have something that's concave up on that interval. Okay, well, if that's the case, now let's try the one between negative 2 and negative 4/3. Well, if you went negative 5/3, that would also get us to see what values we're looking at. Well, negative 5/3, notice when we plug that into 6x plus 8, you'd get negative, or so 6, let me write that out. So if we have x equals negative 5/3, you get 6 times negative 5/3. So you got to be a little bit more careful here. Plus 8. So notice that would be 2 times negative 5 is negative 10. Plus 8, that makes a negative. That's all we care about, is the fact that if it's negative or positive. So you have negative times a negative, so up top you'd have a positive. Now negative 5/3, notice that's down below, we'll have a negative, and then we'll have a positive because negative 5/3 isn't quite 2. So that means this whole thing is negative on that interval. So it actually does switch signs. Okay. So now for our next interval, from negative 4/3 to negative 1, that's going to be a little bit trickier yet. But we can take x equals negative 7/6 and see what happens. Well, notice that's a little bit more interesting because you have negative up top, but then negative 7/6, you multiply that, 6 times negative 7/6 gives you negative 7 plus 8, which is positive 1. And actually everything from there on out will be positive. So you have negative over positive. Now negative 7/6 down below, notice that will be negative in this position, but for the negative 7/6 plus 2, that will be a positive. So negative divided by a negative makes a positive. So this interval here is going to be positive, meaning it's going to be concave up on that interval. Wowzers. So last but not least, pick some number greater than negative 1, so you can use x equals 0. And if you plug that in, notice you'll get positives for everything down below, but you'll get a positive up top but times a negative, so that means this whole interval is negative. So that tells us that we have concave up on the intervals negative infinity to negative 2, where it's undefined, and from negative 4/3 to negative 1. So that means actually negative 4/3 is a point of inflection. So no longer possible, this is a point of inflection. Okay, because we changed concavity there. So now I think we're pretty much ready to draw this thing. Hopefully you all can follow along. Now remember, a couple other things. We have, as we go to positive infinity into negative infinity, we're going to have y equals 1 as our asymptote, and that came from this part right here. So now let's draw this little shindig here. So we're coming, now think about this, we're increasing, we're concave up, we are coming from the point of an asymptote at 1. So you're either on this side or this side, so let's pick which side we're going to be on. Well, notice as we approach negative 2 from the left, we have to be approaching positive infinity, right? So that's telling us which side of the asymptote we'll be on. We'll be coming from this top side, and we're concave up like a cup, and so we're going up and up and up that way. Okay, so one down, right? Now for our next bit, we want to go all the way to negative 4/3, and notice how this negative 4/3, luckily we have this thing lined up is kind of the main idea. Try and line those things up so it's easy to follow what you're doing. So on this next little interval, oops, if I can draw that line straight on down, and then we can draw it down from -1. Even though there's not an asymptote there, we have the point on the graph where there's a solid dot. So on here, -2 from the right hand side, notice we have it's coming from -infinity. But we need to go and hit this point at -4/3, increasing the whole time, but concave down. That's not going to be too bad. Oh, sorry about that. Little. Let me try and shade that in a little better. Okay. Sometimes this pen has a mind of its own. Okay, so notice now, what are we going to do? We're going to shift. Oh, and this should be, we have increasing on this whole interval, by the way. This should now be increasing concave up. Okay, so we're going to increase, now we're concave up like a cup. Now, from here, we switch to increasing and concave down. Remember, though, as we approach infinity, we got to approach 1. So first off, we're going to hit this point concave down. Okay. And then from there on out, we got to stay below that horizontal asymptote while always increasing. And there we go. And you can pretend. One's kind of right there. So, taking a look, notice we drew the graph. We didn't touch a calculator. We didn't do any of that stuff. There we go. The only thing we need is just material on these, on what the functions are, what the derivatives are. So now, the derivatives were given in this case because they were kind of nasty to simplify. But also, there's going to be other cases where it's easy to simplify, right? So if you have some sort of polynomial, you should be able to graph that pretty easily. Given the degree is small enough and things like that. So just be aware of how to work these out and kind of go from there. But you can see how we built the whole function just based on the information we know. So this is putting it all together, right? You put the limits, you put the derivatives, things like that, and we have all that information for us. So, okay, now let's see something on the other side of the fence. Find the area of the region bounded by y equals 8 minus 2x, y equals x plus 8, and y equals 0. Okay, so what we're going to do, don't let your eyes fool you, that was a straight line. Y equals 8 minus 2x. So I don't know much, but I can figure out two things real quick. I can figure out the y-intercept, right? So you plug in 0. So y equals 8 minus 2 times 0. And so notice we get y equals 8 out of that. So from there, we'll have 8 as our point. Okay, so that's one point on this graph. And then the other part, what else do we have? Well, we need our x-intercept. So 0 equals 8 minus 2x. So 2x equals 8, and x equals 4. So notice now, we can draw the graph. Right, because we know it's a line, so this is y equals 8 minus 2x. Okay, y equals x plus 8. What does that thing look like? Well, we start at 8, and then remember our other bound is going to be y equals 0, which is just the x-axis. So we'll have to figure out where does it cross over here. Well, that'll be negative 8. That's not too bad. You can just plug in 0 equals x plus 8. And I plugged in 0 for the other value. So notice there's an intersection point right here. It won't always be at the intercepts. That's just kind of lucked out here. So sometimes you might have to set the equations equal to each other. But you get x equals negative 8 is the other value. And so now we have our line. Right, so, and this was 4 right here. So what do we want to do? Well, we want to find what is this area right here. Well, Well, there's actually two different ways to do it. One's very easy. You could have this done in a few seconds, not even having to use calculus, but I want to illustrate with the calculus side of things. So notice we can take our integral from -8 to 0, and what is our equation? Well, notice this equation is y equals x plus 8. So all that means is we have to just do x plus 8 dx plus the integral from 0 to 4 of 8 minus 2x. dx. So notice this equals, well, we'll get 1/2 x squared just by using the opposite of the power rule. You add 1 to the exponent, and then you divide by that same number that's up in the exponent, so that's where that came from. And the antiderivative of 8 is just 8x, so that's evaluated from -8 to 0. Plus our second one, so we go from 0 to 4, it would be 8x minus, so notice it would be x squared divided by 2 and then times that 2, so the 2's would cancel, so you're left with 8x minus 2, or not 2, x squared, my apologies there. So 8x minus x squared, because the derivative of x squared is 2x, and that's where that comes from, evaluated at 0 and 4. Okay, so what does that mean? Well, that means we have 1/2, we'll have 0 squared plus 8 times 0, which that'll be an easy calculation, minus 1/2 times -8 squared plus 8 times -8. Okay, then plus 8 times 4 minus 4 squared minus 8 times 0 minus 0 squared. So notice that part's 0. You get 64 divided by 2 is 32 minus 64. So notice that's -32 right there. But then we have a negative -32, right? So that'll make a positive 32. Then we get 32 minus 16 here, which is just 16. So you have 32 plus 16, and then this part's minus 0. 32 plus 16, so this whole thing equals 48. Okay? Wasn't the only way to do it, though. What do we have? We have the area is a triangle, so 1/2 base times height. Well, what's our base? Well, you go from this distance 8 and another distance 4, so that's 12. So 1/2 12 times, what's this distance? Well, it's 8. You can see that's the height of the triangle. So notice if you take that 1/2 times 8 is 4 times 12, or 1/2 times 12 is 6 times 8 is 48. So we have a couple ways to kind of have done this one. So hopefully that makes sense on that problem. If not, let me know. That's what I'm here for. So I don't see any questions popping up, so we'll move on to something a little bit more fun. Okay, so runners stand at first and second base in a baseball game, and then at the moment a ball is hit, the runner at first base runs to second base at 15 feet per second. Simultaneously, the runner on second runs to third at 20 feet per second. How fast is the distance between the runners changing 1 second after the ball is hit? Wowzers. So, and it says the distance between consecutive bases is 90 feet. So, bring our little baseball diamond here. We have right angles everywhere around. Okay, so you have this person on first base running this way, and this other person will draw in red, runs to third base. They're running a little bit faster, so we'll put them out there. And so what we want to do is we want to kind of look at this distance, and we'll see how that's changing. Well, we know that the person running in this direction, so we want to try and have a value be something nice from that corresponding point. So we'll call this point X. Okay, so this distance from here to here, wherever that person is, certain time. And because it's changing, that's why we need to use a variable. And then on this person, they're also changing, so we'll call this distance, they're running away from second into third, so we'll call that distance y. That'll make our easy calculation in terms of when we have time involved. So that means if this is x, and then we know this total distance here is 90 feet, that means the distance from here to here is 90 minus x. And so notice, and we got to call this distance between the runners something. Usually I'd use d, but I don't think that's going to be a good idea because we're going to be having derivatives involved. So I'll just use L for length, the length between the runners or whatnot. But you can call it whatever you want. If you want to use d, just don't confuse it when you're using this d for the derivative and whatnot. Okay? So now, setting up an equation that relates these things, right? What do we have? So we have a diagram, everything's drawn, things look nice, hunky-dory, right? We want to try and have an equation where we can start to calculate some things. So what are we looking for? Well, how fast is the distance between the runners changing, right? So that tells us right there. We're looking for dl dt. So we need something to get involved, and we have some things, right? The 20 feet per second, what does that represent? So what are the givens here? Givens are, so the runner from first base runs to second base at 15 feet per second. So that's going to be dx dt equals 15 feet per second. We're going to have dy dt, right? That's going to be the 20 feet per second. That's the runner from second base to third base. Okay? And the rest is drawn in our diagram in terms of our variables and things like that. So now we just need an equation that relates all these things. And the equation, I mean, if you look, we have a right triangle right there, so you can't really go wrong, right? So we know that L squared equals 90 minus x, the quantity squared, plus y squared. Okay, so what we want to do though, we want to solve for dl dt, so we're going to need to take the derivative with respect to time on everything. So that means we take d dt of L squared, and then we got to take d dt of 90 minus x squared, and then plus y squared. So remember, this is a chain rule. So what we have is we have 2L times dl dt, okay, equals, well, we'll have 2 times 90 minus x, but then it goes negative dx dt, right, and then plus 2y dy dt. So if we want dl dt, all we need to do is divide everything by 2L, right? So get 2, 90 minus x, negative dx dt, plus 2y dy dt, all over 2L. And you might notice at this point, so hey, all those have a 2 in them, so we can cross off the 2's. The 2's aren't necessary anymore. So now what we need to figure out is what's x, what's y, and what's L. Okay, let me actually use a different color here. Alright, so we know that this time that we're looking is 1 second after the ball is hit. Well, if it's 1 second after, you take the time it takes, so 15 feet per second, times the 1 second. Notice we're left with a distance, right? So 1 second, and so that equals 15 feet, right? So we have this thing equals 90 minus 15, right? So which would be, that tells us that this distance must be what, 75? Okay. And then negative dx dt, so that's going to be negative, what is our distance from first to second? We already had that, 15. So it's negative 15. Okay, then what's the next piece? Well, we got plus a y. Well, what would y be? Well, notice y would be just taking the 20 feet per second and multiplying by that 1 second, which equals 20 feet. So this distance is 20 feet right here. So we'll have plus 20 times another 20. So what does L equal? Well, that's not going to be too bad either. I'll erase that piece. Hopefully everyone had that, what we're looking for. And our givens now, we don't need those for right now. Okay, so L. Well, we know that L squared equals, just from this equation, it would be 75 squared plus 20 squared, right? And well, maybe we can break that up just a little bit for ourselves. So this would have to be equal to, I think we could write this as 5 times 15 squared, right, plus 5 times 4 squared, which equals 5 squared times, because you have a 5 in both of those, you have a 15 squared plus a 4 squared. No one ever claimed it's going to be a pretty one, but so what do we get? We get L equals, it'll be the square root of 5 squared, and then what's 15 squared? Well, that'll be, so 158 plus another 75, I believe, so that's 225 plus 16, so that's 231, 241. So 5 squared times 241, and I don't believe that's a perfect square, so we could write this as 5 times the square root of 241. So this whole thing became 5 times the square root of 241 down below. So you have 75, and I'm not so concerned on the final answer. That's not a big deal, to be honest with you. So easy way to write this is you have 20 squared. So you have 75. Well, actually, let's do this. If you do want to simplify a little bit, notice you can take the 5 into both of those. So you'll have a negative 3 here, and then you'd have a 4 here. So you'd have 75 times negative 3 plus 80 all over the square root of 241. And so what does that make? Negative, so that's going to be 150 negative 225 plus 80. And so that would be negative 145, I believe. Yeah, something like that. You could leave it right here, to be honest with you. But just to hit the point home, we're actually decreasing. So we have negative 145 all over the square root of 241. And this will be in feet per second. So whatever answer that comes out to be. Right? So it kind of gives you an idea, though, how you can work it out and find your solution and whatnot. So hopefully that gives you some ideas in terms of how we'd set this up. Basically try and make it into an equation that you can use and go from there. That's what we're kind of looking for. Alright, so now moving on, we'll do an optimization one. You have a boat on the ocean. Okay, so I guess we have a shoreline here. So here's our shoreline. It's 4 miles from the nearest point on a straight shoreline, so don't let your eyes fool you, that's a straight shoreline. So here's our point. Let's call it P. We know our boat. That's a beautiful drawing of a boat. I'm sure Picasso would be jealous. So that's 4 miles is that distance. In this boat, what does it say? That point P is 6 miles from a restaurant. So we'll have a beautiful establishment right here. We'll make it a rooftop bar up there too, just for kicks. And we'll draw a few windows. So that way people can get excited about this. So there's your restaurant. Okay, in this distance from here to here we know is 6 miles. Alright, a woman plans to row the boat straight onto the shore and then walk to the restaurant. So we don't know where the woman's going to land, but she's going to land somewhere, and she's going, X will be this distance, and then that means we'll have also Y be this distance, and that makes this distance here 6 minus Y. Okay, so a woman plans to row the boat to a point on the shore and then walk along the shore to the restaurant. So she walks at 3 miles an hour and rows at 2 miles an hour. So write that down, rows at 2 miles an hour, walks at 3. Which point should she land to minimize? So in this case it's an optimization. So minimize total travel time. Okay, so in order to do this, first off, when you're minimizing or maximizing, we need, for right now, actually you'll learn later on that you don't need just one variable, but only one variable. Right? There's going to be some other ways later on when you get to Calc 3. You'll learn some other optimization techniques. But so for this case, obviously we're going with just only one variable. So how do we get this equation down to one variable? Well, this is going to be a right triangle, so that means that y squared plus 4 squared equals x squared. That means that x squared, or minus 4 squared, so x squared minus 16 should equal y squared. And that means, since we're talking distance, it's only the positive version, so we get y equals the square root of x squared minus 16. So that means that this distance from here to here, so from our walking distance, we can rewrite. And so I'll rewrite it in terms of the variable. So this goes 6 minus the square root of x squared minus 16. That's important, right? So if we want to minimize the travel time, right, we need an equation for time. Well, the one thing you might recognize is that we have that speed should equal distance divided by time. So in other words, we get time equals distance divided by speed, and that's going to be important to us. So we'll call this time t of x, I guess. So this represents time in terms of x. So first off, when we're rowing, what's happening? Well, if you notice, we have distance as x, and we want to divide by our speed. Well, what's our speed when we're rowing? Well, rows at 2 miles an hour. So x divided by 2. Okay, that wasn't too bad. So now for our next gig, what do we have? Well, our distance would be the 6 minus the square root of x squared minus 16. Now the way I set this up, actually, to be honest with you, I probably should have solved for x and left this as 6 minus y, but hindsight is always 20/20. We'll see how ugly this turns out to be. So because 6 minus y would be a little bit easier and have the square root appear on the x portion of the triangle. But same difference, so we're wondering at which point on the shore should she land and minimize, so we could have just found y that way. But we'll get there nonetheless. So just a little FYI, there's multiple routes to get there. So hopefully this makes sense at this point. Now what do we need to do? Well, we have time in terms of x. I'm going to erase that part so we have room to finish up the problem. What we're going to do is just take the derivative. So t prime of x. Well, okay. This thing should then be just 1/2, right? Because this is 1/2 times x essentially. And this next piece, we have 6 over 3, which that's gone. That's not going to make a difference. So all we're left with is minus 1/3 times the derivative of that function square root of x squared minus 16. So that would be 1/2. It goes x squared minus 16 to the negative 1/2, which we'll talk about in just a second. And then this is times the derivative of the inside, which makes it a little bit more fun at least. So we'll have the derivative of the inside function is going to be 2x. Okie dokie. So now what we do all the time is set that thing equal to 0. So we go 0 equals 1/2 minus, let's try and brush this thing up a little bit. So the 2's will cancel, so that's nice. That was convenient. And so we'll have an x up top, and down below we'll have a 3, and we'll have a square root of x squared minus 16. Yippee, right? So moving forward from there, what actually happens? Well, move that x and all that other junk over to the other side. So you get x over 3 times the square root of x squared minus 16 equals 1/2. You can do the whole cross multiply thing. And so we get 2x equals 3. So when you go 1 times that, it just goes 3 square root of x squared minus 16. Or in fact, I mean, we want to get rid of the square root sooner or later. So let's set that up so it's going to be pretty nice for us. So we'll make this 2/3 x equals the square root of x squared minus 16. So now when we square it, we're going to get this extraneous solution. Oh, and by the way, just a little FYI, x is greater than, x can't be negative, so we have x is greater than 0. You can also kind of figure out if this whole distance, if we had 6 here and 4 here, we know that x is, well, the largest we could get would be the square root of 4 squared plus 6 squared. So just a little FYI in terms of where our solutions are going with this thing. So now, looking at our equation here, you get 2/3 x squared, that quantity squared, equals x squared minus 16. And we might have picked up an extraneous solution from squaring both sides, so just an FYI there. So that makes 4/9 x squared equals x squared minus 16. Alright, well, add the 16 over and subtract the 4/9 x squared. That makes 16 equals 1x squared minus 4/9 x squared makes 5 over 9 x squared. So moving forward from there, what do we get? We get 16 times 9/5 equals x squared. And so usually you'll have a plus or minus, right? So x equals plus or minus the square root of 16 times 9 divided by 5, right? But notice we have our domain, this has to be greater than 0. So we get x equals, this should be the square root of 16 is 4, so we have 4 times 3 all over the square root of 5, so that'd be 12 over the square root of 5. And we only need the positive version. Just to double check, we'll have 0 on a number line, right? And then we have this 12 over square root of 5 appearing right here. If these are our x values, remember this is an open circle, and we can stop it at the other end, but at the end of the day, here's what we have. So this is equal to 0. We want to look at f or t prime of x, I should say. That's a capital T, don't let your eyes fool you. So t prime of x. Pick a number between 0 and 12 over square root of 5, right? So if you try and do that, square root of 5 is something like 2. So if you pick the number 1, for example, we could plug in 1 in for the x, and we should be able to find out, is that going to work or not? So going back to our equation right here, did we do something? Yeah, I got to double check actually. So I made a bit of a mistake. I got kind of lazy with the domain. It shouldn't have been just 0. To be a little bit more precise, so we can't use 0. We can use 4. You have 4. You have to go straight on down to get there, right? You have 4 miles just to get back to the shoreline. So 4 would be a value that will we can plug in. So number between 4 and 12 over square root of 5, so it would be 5, for example. So if I plug in 5, notice I get 5 squared minus 5 squared minus 16, that's going to be 9, right? So that makes, this is 1 over the square root of 9, right? So we have 1 over the square root of 9 times 5. Okay, and then we have 1/2 minus 1/3 times this. So this is 1/2, and then this would be 1/3 times 1/3 times 5. So that's going to be 5 over 9. So 1/2 minus 5 over 9. So notice, what is this thing? Well, it's going to be negative at the end of the day. So we have a negative value there. Now picking a number bigger than this and smaller than 4 squared plus 6 squared. So what is that going to be? 16 plus 36. So it's going to be 42, 52. So you could use 7 would be your other value that you could plug in. Kind of get a ballpark idea as to what's going on. But notice if you use 7, so we get 49 minus 16, so that'll be 33, I believe. So you have a 33 going on there, and so we'd have 1/2 minus 1/3 times 1 over the square root of 33 times 7. Okay, so now we got to compare this. Is this going to be bigger or smaller than 14? Well, 33 is between 5 and 6, right? Or square root of 33. So this number, at the worst case scenario, will be 1 over 15. But times 7, 7 over 15, that's less than 1/2. So this thing is going to be positive because the 1/2 is greater in this case. So notice we go from decreasing to increasing. That means this is a local min, right? And in fact, since you have some starting point and some ending point, and you have a local min in between on this interval, you know that that will be the minimum. Okay, so that's the x value, but we want to know, what was it, at which point on the shore should she land to minimize that value. Okay, so we have 12 over square root of 5, we just plug that back in into our y. So y equals the square root of 12 over the square root of 5, the quantity squared, minus 16. So whatever number that is, that's 144 over 5, and you can go about your business and get your final answer that way. But at the end of the day, we have our answer that we're looking for. So hopefully that makes sense in terms of, oh, and this should be in terms of, what is this? Miles. Miles from P. So that way we have our labels. Okay, so you've seen an optimization, you've seen a related rates, and now let's make sure we can hit home what kind of is the purpose of relating all these things. Let f of x be a continuous and differentiable function with f of 5 equal 4, and the tangent line to f of x at x equals 5 is given by y equals 10x minus 42. If h of x equals f of x raised to the 4th power, then find h prime of 5. So first thing, let's find h prime of x. Well, notice we got to use the chain rule. So that means we got to take the derivative using the power rule. 4f of x cubed times the derivative of the interior function. So times the derivative of f of x. Okay, so this makes 4f of x, the quantity cubed, f prime of x. So now we want to find h prime of 5. So that should be 4 times f of 5, the quantity cubed, times f prime of 5. So f of 5 is given to us, right? So that's going to be 4 times 4 cubed, right? And so what is that? That's going to be, so 4 cubed is 64. And then 64 times 4, that'll be 256. We'll deal with that in just a minute though. So f prime of 5, notice we have the tangent line to f of x at x equals 5 is given by this. That's important because f prime of 5, this is the slope of the tangent line. At x equals 5. Right? So all we needed was the slope of that tangent line, so that's 10. So f prime of 5 equals 10. So 4 times 64 times 10, so that's 256 times 10, that's 2,560, and we are done. Okay, last but certainly not least, let's evaluate an integral, because this question was also asked in terms of how we go about it. So this one's a u substitution. It's a little bit outside the norm. If you go u equal to, and you can always guess, you could try x, you see what happens, but u equals x plus 1 and then du equals dx, right? So there's not much changing going on here. One thing to take note of though, this is x equals 0 and this is x equals 1. So we got to change those bounds, right, to u's. So when you plug in 0, notice you get 0 plus 1 for that new bound when we put it in terms of u. And then we have, this would be 1 plus 1. Now we have an x, but we have a square root of u, and then this changes to a du. So it seems like we haven't made the right choice. But we can actually fix that. Notice from this equation you can also get x equals u minus 1. So that will do the trick for us. So now we have an integral from 1 to 2 of u minus 1, that quantity, times u du. Okay, so moving forward from there, you get the integral from 1 to 2 of, this would be u, what is that, u, yeah, u squared? Oh, I'm sorry, it should have been square root of u. I forgot about that. So yeah, I was about to say, something went wrong there. U to the 3 halves now, minus u to the 1 half. And then we have a du. So now taking the antiderivative, so notice you get, when you add 1 to 3 halves, you get 5 halves. So u to the 5 halves, but you basically divide by 5 halves, which means you're multiplying by 2/5. there. Okay, so then minus, this would be u to the, add 1 to 1/2, you get 3/2. But instead of dividing by 3/2, you can just consider that multiplication by 2/3. And so now we want to evaluate this at 1 and 2. Well, another way to write this, just an FYI, you can write this 2/5. This can be considered u squared times u to the 1/2, or and this one could be u times u to the 1/2. And remember, u to the 1/2 is just the square root, right? So you could write this first term 2/5. You could write it as 2 squared times the square root of 2 minus 2/3 times 2 times the square root of 2. Okay? Minus, well, this next one would be 2/5. Let me make sure all this is in parentheses. Times 1 squared times the square root of 1 minus 2/3 times 1 times the square root of 1. Wowzers, right? Well, when you take a look at this, what do we get? We get 4, that makes 8/5. Square root of 2 minus, this would be 4/3. Square root of 2. Minus, this will be just 2/5 minus 2/3. Okay, in order to do this, we got to get a common denominator. So our common denominator would be 15 in either case. So this makes 24/15 of these. Notice we can factor out a square root of 2, by the way. And then this would be what, 20/15 times the square root of 2 minus, so what would this next one be? We have 15 would be that, so we go 6/15 minus, that'd be 10/15. Okay, so taking that up here, notice we get 4/15 times the square root of 2 minus 4/15. So there's a few different ways to write this, and this is where people kind of freak out sometimes, no reason to. You can write this one way as 4/15 times the square root of 2 minus 1, right? Because you factored out a 4/15 in both terms. Remember, that is the same thing as 4 times the square root of 2 minus 1 all over 15. Right? That's the same thing. And also, that is 4 times the square root of 2 minus 4 all over 15. Okay? And there's other ways you can keep on going. But all of these are the same. They're equivalent answers and whatnot. So you should be comfortable being able to convert. And I don't care which one you give me at the end of the day. So whatever one works for you. So I don't see any questions popping up. So I'm assuming you all have it. Make sure you also take a look at the mean value theorem along with the limits like L'Hopital's rule and things like that. Intermediate value theorem, that pops up quite a bit too. So you can see all that stuff. It's all fair game come exam time. I wish you all the best luck coming up on that upcoming exam, and let me know if you have any other questions in the meantime.